In this video, we're going to talk about exponential growth and decay. So I'm going to start by writing down the equation. A is equal to A naught e to the k t power. You may also see this written A of t, just representing the function notation. So either of those formats indicating the same equation. First thing we need to do is go through this and understand the formula. And you might be recognizing that it looks very similar to the PERT formula that we used for exponential growth in money, or what we say compounded continuous growth in investments or in savings accounts. And that's not just by chance. These pieces are going to line up very similarly. So with our money formula, our compounded continuously formula, the P stood for the principal and the A stood for the accumulated value or the future value. Same idea here, just we're no longer talking about money. This equation can pertain to anything that is growing or shrinking along that exponential growth pattern. So it could be things like populations, it could be bacteria, it could be radioactive substances. Any sort of element that is growing or decaying at an exponential rate is going to follow this equation. But what we just said, that P, talking about principal, that's the starting point. And so the ideas are the same. The A naught is the starting amount, or we can think of as the initial population in the case of population growth. Starting amount, initial population. The A, or the AT, is the end amount. Now that little subscript of 0, it is a subscript, it's read A naught, or A subscript 0. That 0 always indicates an initial, and so that's a good indication that that is our initial, and then our final is over here. But again, this is the same as our money formula, where P stood for the principal and A was the final value. The E's are the same, and then we have this KT exponent, very similar to the RT. The K is the rate, and then the T is the time. I'm not going to go into a ton of detail on why we use K, but this is because many populations grow on what we call a K population growth pattern. Populations have a tendency to kind of shoot off to infinity very quickly, and then they can kind of collapse and kind of wind their way down. That's not meant to be so bumpy in there. So it kind of gives us what looks like a K as they're declining. So that's why we see the K rate, but that is not a something that we're really going to be concerned about in terms of why it's a K. We just want to know how the formula works. Now, if we're thinking that they're the same formula, they are, so why don't I just stick with this formula right here? Well, if you want to, you can. I have no problem with that. Just because we're moving away from money, I'm going to call them by the more general A and A naught rather than P and A. But it is the same formula, so if we want to think about it as the same thing, sure, it still works. So let's put this thing to use. Let's say we have a small island that has seen an increase in population. A small island's population is given by the equation A equals 120 e to the 0.01 t. And we're just going to take this problem, we're going to do a lot of things with it. So we have a small population, small island's population given by the equation A equals 120 e to the 0.01 t. Now, one of the nice things about this equation is it gives us that very definite information every single time. We know that based on its positions, we know what the starting amount is, we know what the rate is, and then we have the variables t that we should just plug in to get the time. So what if I asked you, what was the population at the initial? And I should probably define that. So let's say t is the number of years after 2000. So I need a starting year. It's not just working from some arbitrary year. We need a starting year. So now I know that if I look at that 120, that is equal to the initial starting amount, and we know what year that corresponds to. So there were 120 people in the year 2000. We can also see that this population is increasing. How do we know that it's increasing? Well, that rate up there. We see a growth rate of 0.01%. So it's increasing at 1% every year. So that rate is given to us right in that equation. We just need to remember to turn it into the percentage. So again, very intuitive. We can see right away that the thing is shrinking, growing. If it were shrinking, we would see a negative in front. So negative rates give us a shrinking population, but because we have that positive, it is growing. So now we could do any number of things with this. Let's say we want to find what is the population in 2010. Well, I'm going to take my year and plug it into my t. I'm not just going to plug in the 2010 though, because remember t is the number of years after 2000. So that means I need to be plugging in the number 10. So we'll have 100 times 120 times e to the 0.1 power. And so if we type this into our calculators, let's see what we get. 120 e to the 0.1 gives us an amount of 132.62. I'm around to 2 decimal places. And what was the A talking about? It was talking about the population, so this would be people. We can see that in 10 years, the population has grown by approximately 12 people, or almost 13 people, rounding to 13. What if I want to know when will the population be? Let's say we want it to be 200 people. Well, this time that 200 is talking about the number of people, so I have to plug it into the final amount. We're looking for the time, and so I'm going to leave that variable as just a t there. Now I need to solve this exponential equation, and I do that first by isolating the exponential. So we'll divide over the 120. Next, I need to take the natural log of base sides. I could take the log, but natural log makes more sense because then the e works itself out. And I can also simplify 200 over 120 if I want to. I can clearly knock off the zeros, and then 4 goes into both of those things 5/3. So I'm just simplifying to make it a little bit easier. And then, like I said, the reason we chose the natural log of e, we get just the exponent, so just the 0.01t. And then finally, to get t all by itself, we divide by that 0.01. And so now I'm going to pull out my calculator again. We'll type this in. Let's see what we get. So we'll have the natural log, 5/3, divided by 0.01. When we do that, we get 51.08. And so if we put the meaning behind this, it's not just talking about the year 51, because remember our baseline year was the year 2000. So we would say in the year 2051, the population will reach 200 people. So we always have to remember that the x and y, we've got to tie it to what the problem told us they were. It wasn't just 51, a year of 51, it is 51 years from the starting point being 2000, so we had to add that to the 2000. Let's move on to another example. Let's say we have bacteria in a jar decrease at a rate of 23% per day. If 1,250 bacteria are initially present, how many are there after 10 days? Well, this problem, unlike the last one, we have to write out the equation to solve this problem. They don't give us that equation. So we know we're dealing with exponential growth, or in this case, decay. It's decreasing at a rate of 23% per day. So I know when I'm setting up my formula, I better see that the R is a negative. If I forget to put that negative on there, my problem's obviously going to be wrong. So I want to find the future amount of bacteria. I know the starting amount was 1,250. My rate was 23%. I can't just write a 23 here, because remember that's percent. I always have to work with it in decimal form. So it needs to be a 0.23, and as we just discussed, it better be a negative. So this would be the equation that would give me the amount of bacteria present after any number of days. Or conversely, I could find the number of days it took to reach a certain number of bacteria. We have our initial population in there. That is a fixed number. That is always going to be fixed based on this scenario. We have the percentage that they're decreasing by. That is, again, fixed in this scenario. And now we can use this to solve the problem. So we want to know how many bacteria there were after 10 days. Well, I'll plug a 10 in for my t. A equals 1,250 negative 0.23 times 10. And we can simplify that if we want, or we can just type it all into the calculator in one step. If you're going to do it in one step, just make sure that you're careful. You put parentheses around the entire exponent. So we'll have the 1,250 e to the negative 2.3 times 10. And when we do that, 0.23 times 10, we get 125.32. And again, these are bacteria. And that would be the number of bacteria present after 10 days. Let's move on to a couple other terms. Those are half-life and doubling time. Half-life and doubling time. Now, these seem like they should be pretty easy definitions, and I think they are, but I'm going to bother to define them because I always see some careless mistakes, especially with half-life. So the half-life is the amount of time for the population to reach half of its initial. The doubling time, it's going to be the same sense, but it's going to be the amount of time it takes for the population to double its initial. I said these seem like very easy definitions. I think they make a lot of sense. They're very intuitive, but I do want to emphasize this word right here. Doubling time, half-life are times, and this is the biggest mistake I see. They are in somehow related to the rate, but they are not our rate. They're not giving us that actual K value or the R value, depending on how we define that rate. It is giving me amount of time. So let's see how we can apply this. If the half-life of carbon 29, just making up a random one so I can make up a random half-life, is 28 years, how many years does it take for only 30% of the initial carbon 29 to be present? Like I said, carbon 29, I'm not a chemist, but I've just made that up. So now I don't know what its half-life is, just making up a problem here. So don't hold this against me, chemistry majors. So here we have our substance. We are being told that it is It's got a half-life, so we know it's decaying. We are told what that half-life is, but it seems like I'm given very few details here. I see a percentage, but that's not actually my rate. Notice that's how much we want to be left, so somehow that's related to my A, not my rate. Don't assume that anytime you see a percentage, it's a rate. It's probably the biggest mistake I see on these problems is assuming percent is rate. That 28, my half-life, that's going to be a very important number. That's going to help me solve a lot here. So let's write out what we actually want to know. I want to know how long it takes for 30% of the initial carbon to be present. Do I know how much was present initially? No. So let me call it A naught. I don't know how much is present initially, but I know I want 30% or 0.3 of that initial amount. Do I know the rate? No, I do not. Do I know the time? No, that's what I'm looking for. So it seems like I have a lot of unknowns here, and I do. Now, if I were to solve this problem, the first thing I do is I divide both sides by A naught. And when we divide both sides by A naught, we'd be left with 0.3 is equal to e to the kt. Another way I say sometimes to do these problems is just pick an arbitrary number for your starting amount. Let's say we picked 1 for your starting amount. If you start with 1, and we want 30% of it, we'd have 0.3 left. Why does that work? Why can't I just pick any number? Well, let's choose a different number. Let's say we chose this time 100. Might be easier so we don't end up with fractions. If I start with 100, well, what is 30% of 100? It's 30. What would be my first step? Dividing the 100 over. When I divide 100 over, what do I get over here? I get 0.3. That's the same thing we had just a second ago. What if I started with 8.2? Well, here I'd have whatever 30% of 8.2 is, and then the first thing I'm going to do is I'm going to divide off that 8.2, meaning I'm back to a 0.3 there. So this is kind of the more formal way to approach it. We have 30% of the initial. We don't know what that initial is. We immediately divide off the initial, and so we have 0.3 left. But we could have actually started with just any number, found 30% of it, and that's kind of simplified to be the same 0.3. We're always going to get that 0.3 is equal to e to the kt. Now, that's a little bit of a side note there, but let's get back to the problem. This is what we want to solve. We want to figure out what that t is in order to get that 0.3 on the left-hand side. Problem is, I don't know what k is. And that 28, that's not giving me my k. Like I said, one of the most common mistakes I see is just taking that 28, plugging in for k. But it's not. It's a time. And I can't plug it in for the t here because then we're looking for the time it takes to get to 30%. We're not saying that it takes 28 years to get to 30%. So we actually have to start with another problem. We're going to set up the problem based on this 28. If I were to plug in 28 for my time, so 28k, then I should have a half of whatever I started with. So we can do kind of the same logic here. I could choose a starting amount of 1. That would mean I'm down to 1/2. I could choose a starting amount of a naught, and that would mean I'm down to 1/2 of that a naught. I could choose 8. Well, half of 8 is 4, but any which way I do it, if I divide by that a naught at the very start, I'm down to the equation 1/2 equals e to the 28k. Now I need to solve this for k. So I'm going to take the natural log of both sides. And so my k, when I divide by the 28, is going to be equal to the natural log 1/2 over 28. If we were to type this into the calculator, we'd get a decimal approximation. We better see that it's negative. We will get a negative because the natural log of a fraction is always negative. But I'm not actually going to type it into the calculator yet because this is not my final answer. This is what I had to do in order to solve this equation to the right. So I'm going to wait to round this until I actually solve the equation that I wanted. So let's plug this in now. 0.3 is equal to e to the natural log of 1/2 divided by 28 times t. And so just like we said a second ago, to solve this, we're going to have to take the natural log of both sides. Natural log of 0.3 is equal to natural log of 1/2 over 28 t. And then to get t by itself, we could divide or we could multiply by the reciprocal. I prefer to multiply by the reciprocal. So we'd have 28 natural log of 0.3 over the natural log of 1/2 equals my t. And so now, because this is the thing I actually want to know the answer for, I'm going to type this into the calculator. 28 natural log of 0.3 divided by the natural log of 1/2, and we should get a t-value of approximately 48.64 around 2 decimal places. And so what this tells me, remember what our units were. Half-life of carbon-29 was 28 years, so my time variable is clearly years. We wanted 30% to be left, so what this tells me is it's going to take 48 years for 30% of the initial carbon to be present. That would make sense. If the half-life is 28, it better take longer than 28 years. And remember how these half-lives work. It's going to decrease less and less each time because we just have less to go down by. So 48 makes a lot of sense in the context of this problem. We're using these exponential and logarithmic equations in the same way as we have been doing. We're following the same steps to solve them. The only difference is now we are having to create those equations. And we create those equations by using that same equation. A is equal to A naught e to the kt. We just have to think about, do we know our starting amount? Do we know our rate? And if we don't, well, is there some other information that can help me get there? In this case, we'd had a half-life. Maybe we're told that after 30 years, we'll have 15% present. We can use that to our advantage as well. But the key is we are basing everything on exponential growth and decay off of this equation.